Okay, good morning, guys. So yesterday we started well, not started, I guess. We've done this a couple weeks ago, but we continued modeling quadratic equations and modeling what we call the vertical motion formula, right? Modeling acceleration due to gravity. Yesterday was specifically what happens if you drop something. So we started by dropping things on Earth. We looked at, I think, maybe a slide that we didn't do about dropping something on the moon. We did one about dropping something on a much heavier, denser planet where there would be more gravity. Today we're going to take the next step, which is going to be actually throwing the object up in the air. So we said, let's take a look at this one, right? So it says a ball is tossed in the air from a height of 80 feet with an initial upward velocity of 64 feet per second. The following equation models the height. So just to go back over what we talked about yesterday, the constant represented the initial height, right? So this is a person who's already 80 feet in the air, so maybe on top of IS 125 or something like that. That's about 80 feet high. And they're throwing something straight up in the air, right? Again, not at an angle or something. That would be a little bit more challenging, kind of more of a physics lesson. But we're throwing this straight up in the air from 80 feet. 64 represents our initial upward velocity. And we say initial because as soon as the object leaves our hands, the velocity slows down because gravity starts to pull it down and starts to decrease its upward velocity. And again, this doesn't, if I was doing this in the classroom, I'd show you throwing something up in the air and we talk about what, we actually see the vertex and things like that, but we're kind of limited here what we can do remotely, and that's okay. But just so we understand, right? So this is always if we're talking about feet per second as opposed to meters, which would be negative 4.9. That's the speed of gravity on Earth, right? This is, again, our upward velocity, the speed we throw it up at, and this is our starting height. So the first thing we're going to do is we're going to grab our table. So we are going to put this in our calculator as is, except instead of t, we're going to use x, right? We're going to use the variable button that we've been using all year. This should be nothing new. So I'm going to put the table here, and then I'm going to wipe it out because I have a lot of questions to answer, and you guys have your calculators at home that you're using for this. So this is what I've got, right? At time 0, the height is 80. At time 1, I've got 128. At time 2, I've got 144. At time 3, I've got 128. At time 4, I've got 80. And time 5, I've got 0. So something we need to talk about that we didn't have to talk about yesterday is what's called our vertex, right? So we said when we're graphing any parabola, whether it's a real world situation or whether it's just, y equals x squared minus 2x plus 5, there's going to be a bunch of repeated y values, these symmetrical y values, and there's going to be the one unique y value in the middle. We call that point the vertex. And when we did this in class, I kept saying things like this will have significance when we do word problems and when we model quadratics. Now yesterday, we didn't really need to talk about the vertex because the vertex was always our starting point. So I didn't, it wasn't significant because we didn't look at the negative side of the graph and we didn't look at the negative side of the table. Here it is going to be significant. So just from a real world perspective, the vertex is where the ball peaks. It's where the object stops moving up and begins to start moving down. So for a certain amount of time, the object is moving straight up, right? I'm doing this now, you can't see me, but imagine, maybe you yourself take a pen or pencil, whatever you're taking your notes with, and throw it straight up in the air. And you see that it goes up and up and up, and as it goes up, it slows down. It hits its maximum point for a fraction of a second. You can consider it stationary, and then it starts moving down. And the interesting thing about this is that whatever the speed is when it leaves your hand is the speed when it touches your hand if it comes straight down. Again, neglecting things like wind resistance and stuff like that. So in this example, right, it's going 144 feet in the air, which is pretty high if you're throwing something. But if you're throwing this object really at 64 feet per second, it's going to hit your hand at 64 feet per second. The same speed it goes up is the speed it will be when it comes down. All right, that's just kind of an aside. So let's talk about this graph now. So I've got 0, 80. So I already labeled the graph just to save ourselves a little time here. So I've got 0, 80. I've got 1, 128. I've got 2, 144, which goes off my graph a little bit. My graph only goes up to 140, but I was a little bit limited there. I've got 3, 128. I've got 480. And I've got 5, 0. So we really have a nice sense of symmetry in terms of that these 2 points and these 2 points are going to be at the same height. And again, you would kind of see that if you were to, kind of video it or take stop action or something like that of the object going up and down. It'd be really interesting to see. So I'm going to try to make this as smooth a curve as possible. I apologize, that's not especially smooth here. Yeah, so it's going to look something like that. So I'm going to label my equation. And there's a lot of questions that I'm going to answer about this. So I'm going to get rid of the table. As I said, you guys have this in your calculators already, and you should be taking notes. Again, we may have some of those notebook checks coming up again. So what's the vertex, right? So we looked at the vertex already, which is 2, 144. What does it represent? Well, it tells us two different things. I mean, they're tightly interconnected, but they're two different things. What does the 2 represent? Well, let's talk about the 144. The 144 feet is the maximum height that this object reaches. So that's the first significant piece of information. We're throwing something up, we're 80 feet in the air. How high does it go? Well, the answer is it goes a maximum height of 144 feet. And when did it reach that maximum height? It reached that maximum height at 2 seconds. So this is something that has always really been on the Regents about what's the vertex and what 2 things does it represent. And we need to, and this will be in the homework too, we need to understand both of those things. That it represents A, the maximum height that the object reached, and B, it represents when it got there. And that was 2 seconds in, right? How long was it traveling? Well, we'll get to that, I guess, at the end, right? So what does the vertex represent? Okay, we talked about that. When is it ascending? Well, let's see when it's ascending. This is going to be slightly different than what we did yesterday. So yesterday we talked about the domain and range, and I had the or equal signs under here yesterday. I'm not going to have them today, and it's kind of a fundamental question. We usually have a really good discussion about this in class. Why am I only say it's ascending between 0 and 2, not including 0 and 2? So we're not going to use an or equal sign because technically at 0 seconds, the ball isn't going anywhere, the object isn't going anywhere. And at 2 seconds, it's not going up or down, right? It's peaked, right? So it's technically stationary for that fraction of a second. So it's only going to be ascending or going up between 0 and 2, but not inclusive. And when's it going to be going down? Well, we'd say kind of the same thing, right? At 2, it's not going up or down, and this is t, and it looks like a plus, that's a t. What about at 5? Well, we're going to get to this in a minute, but at 5, the ball's on the ground. So at exactly 5 seconds, the ball hits the ground. So at time 5, it's not going up or down. It's stationary. It's on the ground. Now, as far as our domain, the domain are the valid x values that we're going to use. Now, that's going to be 0 to 5 inclusive, right? In other words, 0 is in our domain. Just the ball's not going up or down. Same thing with 5. Now, what about the range? Well, we're going from 0. And again, this is going to be h of t, which is like your y variable. And that's going to be all the way up to 144. Now, that's a little strange, right? Because I know sometimes we put like 0 to 0 because it goes up from 0 up to 144 down to 0. But we want to know what are all the possible y values of this ball. Well, there's a point where this ball is 100 feet off the ground, and it's here. There's a point where the ball is 72 feet off the ground, let's say, or 43 feet off the ground. There's no point when it's negative 10 feet off the ground, and there's no point where it's 200 feet off the ground. So this is our range. These are our possible y values, or h of t values, and this is our domain. How long will it take the ball to land? Well, that's like the easiest question of all. It's going to take it 5 seconds. Now, as far as solving algebraically to prove it's correct, well, what I would do is I'm going to do this kind of quickly. Since we'd set this equal to 0, I'm going to divide both sides by negative 16. And if I divide both sides by negative 16, I end up with t squared minus 4t minus 5. And if I factor that, I get t minus 5 times t plus 1. Now, I don't have a whole lot of space here, but when I use zero product and split this up, I get t is 5 and t is negative 1. Now, why is it t is negative 1? Well, if you really looked at the graph in your calculator, at negative 1, it would actually complete the rest of this nice, perfectly symmetrical parabola, but time negative 1 doesn't exist. So obviously that's going to be rejected, and we can prove, as we've figured out here by looking at the graph, that it's going to take 5 seconds for this object to land. All right, and we should be able to do the same thing here pretty easily, right? So now it says we've got a bullet that's being shot in the air. So obviously the bullet's going to be going much faster, right? 320 feet per second is very fast. And it's going to take it a lot longer to land because it's going to reach a much higher maximum height. So again, we're going to put this right in our calculators. We're going to look at time, and we're going to look at height as a function of the time. And I'm going to go by 5s here. Right? I don't need to plot all 20 of these values. So we have 0, 0. Oh, so I should have pointed this out, right? The bullet shot from the ground. So that's the only, not the only thing, but that's one of the differences between this one versus the last one, is that the initial height is 0. So it's kind of like what we talked about yesterday and kind of like what we talked about today, except yesterday we were dropping something. Now we're shooting something up in the air, and this one is from the ground. The other one was from a height of 80 feet. All right, so these are the values that I'm sure you guys are going to pull from your calculator as well. So we have this nice, really obvious symmetry that we're used to seeing, right? 0, 0, 1200, 1200, and clearly our vertex is going to be right here at 1600. All right, so let's answer this question, right? At what point does the bullet reach its maximum height? Well, it reaches its maximum height at 10 seconds. What is that height? Well, that height is right here, and that height is 1600 feet. All right, so now let's take a look at the graph. So I've got 0, 0, and I've got 20, 0. I've got 5, 1200. This is going to be a much easier one to graph. And I've got 15, 1200. And then I've got my vertex there, which is 10, 1600. All right, so this is a much easier one to graph. We see all the symmetry because it doesn't start at a predetermined height. It starts at the ground, right? And we're going to label. I don't have a lot of space. So I'm just going to kind of drop a little arrow there to show that I'm labeling it. So let's talk about when it's ascending. Well, again, it's ascending for the first 10 seconds. So we'd say 0 less than t less than 10. So it's ascending. And again, at 0, it's not going anywhere. It didn't start yet. At 10, it's at its maximum height. It's not going up or going down. It's stationary. So we'd say between 0 and 10. And when is it descending? Well, it's descending between 10 and 20. Again, at 20 exactly, it's on the ground, so we don't use the equal sign there. At 10, we just said it's not going up or down. What is my domain? Well, my domain are all the valid x values, or t values in this case, which is anything from 0 to 20 inclusive. So where's the ball at time 0? It's at 0 feet, but that's a significant point. We need to know that it started on the ground. Where was it at 1? Well, we can sub in 1 and we get something like 304. We could sub in 2. We can sub in everything up to 20. If you sub in 25, you're going to get a negative answer, which is not valid, right? The ball doesn't come down through the floor. And as far as the range, we need to just look at the maximum height, and we need to look at the minimum height. So we'd say 0 is less than or equal to the height, h of t, and that's less than or equal to the maximum height, which is 1600. How long will it take for the bullet to land? Well, that should be very easy. We get that from the table. We can get that from the graph, or we can solve the equation. So if I wanted to do it algebraically, I'd go back to the equation. I'd divide everything by negative 16. I'd get 0 equals t squared minus 20, t. I'd factor that as, not that we need to do it this way, but I'd factor that as t times t minus 20. And then I'd set each of these equal to 0. I'd say t is equal to 0 and t minus 20 is equal to 0, which would give me t equals 20. So I didn't ask you to do it algebraically, but we should know that you can always do these algebraically by setting the height equal to 0 and solving the quadratic equation. And now we know that we can also use the quadratic formula since we did that last week. All right, so there's your now try, guys. So as always, especially for your notes, it would be a good idea for us to try this on our own. So let's take a look at what our table should look like here. I've got my t and I've got my h of t. This one I should go out to 6 seconds, which I'm sure you'll see on your calculators as well. All right, so that's what that graph should look like. So I had gone, I don't know why it got cut off, but I had gone by 25s here. All right, so I'm not going to worry about the graph, but it's going to start at 0, 192. It's going to peak at our vertex, which is right here at 2, 256. And from that, we should be able to, and again, you'll see the graph in your calculators. From that, we should be able to answer these questions, right? At what point does the ball reach the maximum height? So with the first question, I asked you for the vertex, and I asked you what two things it meant. This is kind of the same thing, just in a more roundabout way. At what point does it reach its maximum height? So we'd say it reaches its maximum height at 2 seconds. And what is that height? We'd say that height is 256 feet. Now, the next question is, when is our ball ascending? So it's going to be ascending, right, between 0 and 2. Again, at exactly 2 seconds, it is stationary. It's about to head down, and it just stopped heading up. When is it going to be descending? We would say from 2 to 6. And again, that is not inclusive. At 6, it is on the ground. It is no longer descending. What is my domain? So my domain is going to be all of my valid x values, or in this case, they are t values. So from 0 to 6. At 0, our experiment is about to start. At 6, the ball hits the ground. Our experiment is over. What is our range? Well, the range of the possible y values, or h of t values. So this is my max, right? So I'm going from 0 all the way up to 256. And then it says, how long will it take for the ball to land? Well, that's a nice, easy question. It will take 6 seconds. And it says, solve algebraically to prove your solution is correct. So I can do that on the next slide, since I haven't really done too much of that in too much detail here. I've got negative 16t squared plus 64t plus 192. So I want to divide everything on both sides by negative 16. That's going to give me 0 equals t squared minus 4t minus 12. I could factor that really easily as t minus 6 times t plus 2. Now I'm going to split it up. I get t minus 6 equals 0 and t plus 2 equals 0. So I get t equals 6. And of course, I'm going to reject my negative solution because time cannot be negative. And as we showed in our table, and as we would have seen if I would have had space for my graph, it's going to take us 6 seconds for the ball to hit the ground.